Hi, this is Shelley Physics. I'm doing a Math Supporting Physics episode on Calculus Express integrals. If you have some time to read over the introduction to this worksheet here, please do so. But the main highlights include um, when integrating, there are two types, indefinite and definite. Indefinite integrals will give you a function. A definite integral gives you a number. Now that number is really what an integral is. It's the area under a curve, under a function. Now this might seem a little strange, but if you think about our last episode on derivatives, the derivative is the slope or the change in a line. So the integral is sort of like the inverse operation of a derivative. How do you go from the change back to the original function? The indefinite integral will give you that something close to that original function, but the definite integral gives you more of that multiplication of the two axes. So if you think about the slope, it's a rise over a run. It's the y-axis divided by the x-axis. So the integral becomes the multiple of those two, the rise times the run, in essence. But we have to be able to define the bounds of that rise and run of what's important to the problem. All right, so here's the start on the indefinite integral. Observe the two functions below. Now you might remember these shapes from the introduction to derivatives and that they were related. So what if we are starting with the function on the left, which describes the change of a function or change of a scenario, okay? So this is the change. How do we relate it back to the original? So if the function on the left represents the slope values of the new function that we're looking for, there's an issue. Like we might be able to determine the slope. So if we consider this starting value here at x equals 0, this is a positive number. It's greater than 0. And then what happens to these values? They're going to decrease and become a 0 value at this point. So if this represents the slope of a new line, then the slope should start out positive and approach 0. Then it'll become negative and increase in negativity until this point. Then it will decrease in negativity until this point, and the slope will become 0 again. So if we start translating that over here, there's going to be a 0 slope here, a 0 slope here, and then look, as we follow this along again, we're going to get some positive slopes and then another 0 slope. So here's some positive slopes and then another 0 slope at this point. So you see how that translates from the left to the right. But there's a major issue. There's some information lost of sorts. We don't know where that y-intercept is. So with derivatives, we were starting with a function like this and on the right here and going to the function on the left. Let's map out the slopes of sorts. But when you do that, what do you lose? You lose where this function begins. Does it start in the positive territory? Does it start at 0 at x equals 0? Or does it start in a y equals negative value territory? We don't know. So there's always this unknown plus or minus some constant. It could be plus a negative number, or it could be a plus a positive number. So when you're doing an indefinite integral, as we're going to see, we always need to add a plus c at the end, just to consider this function might be shifted up or down, and we just don't know. That information has been lost of sorts or never known. That c also represents an initial condition. If this is a time-based function, if this is a function with respect to time on the x-axis, then this would represent the initial condition at time t equals 0. All right, so just like we learned a power rule for derivatives, we're going to learn the power rule for integrals. This is a common integration rule. If we have a function, we'll say f prime of x here, and it's a function of x, and that x is raised to some n power. All right, so this might look a little funky here, but let me break it down. You might recall for derivatives, if you have a function f of x equals, we'll say 2x cubed. All right, then the derivative, or df dx, another way to, we'll write that also. Derivative of f with respect to x, that means the same thing. We would keep that 2 in front, that coefficient, and we drop this 3 down here, 2 times n x to the n minus 1. 3 minus 2 would be squared. Do you see how that exponent decreases when we take the derivative? And there's the original 3 out front here. Well, when we integrate, if we're to go from this 6x squared back to 2x cubed, then we're going to need to add an exponent number. And to go from 6 back to 2, we would have to divide by 3. So when we integrate with this power rule, we're going to figure out what n plus 1 is. All right, we're going to raise it to the n plus 1, but we're also going to divide by n plus 1. So that's what this is here. Think about what that exponent is. The integral is going to be that value divided by n plus 1, and then we're going to raise the x by 1 exponent, and also add this plus c here. Now there's a note, this doesn't work when n equals -1. All right, you'll get a kind of a different function out of that, and that's where all the intrigue of integration comes in. But that's for another time. So we're going to be dealing with all exponent values, anything but n equals -1. That's what this works for. So if f of x equals x to the 5th power, then n equals 5. The integral is going to be, so the way you write this, there's a little symbol here, we call it the integration sign, but as you might look at it, it looks kind of like an extended and stretched out S. At some level, when you take calculus, you're going to learn the basics of integration. It's kind of like a sum. We're summing area here. You see, this is an f of x. This is like a y-axis times a change in the x-axis. So we're actually finding little bits of area underneath the curve, which I'll come to when we talk about definite integrals in a moment. We're taking all those little bits of area and summing them up. So that is a sort of an S sign there of sorts. But all right, so when we say we want to integrate, we're going to put a integral sign in front of the thing we're trying to integrate and write a dx to say that we're integrating in terms of x. All right, so if our n is 5, then we're going to divide by 6 and raise it to the 6th power. So x to the 5th becomes x to the 6th divided by 6. That's what we're seeing here. So if you'd like to pause this video for a moment and try out 1, 2, and 3. One thing I didn't really talk about here is just if you don't see an exponent, just assume that's a 1 and it should become easy. So pause this video, try these out. Hopefully you've had a chance to pause the video, and your answer should be, if we take an integral of x dx, that will become x squared times 1/2, or x squared over 2. If we integrate x squared dx, oop, what did I forget? I forgot a plus c on there. Okay, don't forget that plus c. So this could be plus 2, plus 4, minus 8. Could be a -8 for c. All right, so we don't want to forget that. Now, getting back to the second one, x squared becomes an x cubed divided by 3 plus c. And you guessed it, for x cubed, we're going to have x to the 4th times 1/4. You could also write it like this, or x to the 4th divided by 4 plus c. Right. That's a little bit of practice. Now on this side, what I've given you just to try to keep the notation from the last activity. If you did the derivatives, calculus express derivatives, you might be used to seeing this f prime x. So here we're starting with f prime x, and we're trying to get back to f of x. Here's y prime x, just to trying to throw around a few different letters, so you're used to seeing them in different forms. So if y prime x is 2x to the 6th power, then we're going to have 2x to the 6th power dx, the integral sign in front, and we'll raise that 6 to a 7. So this becomes 2. Remember that 2 is a coefficient, and it will remain there. So it'll be 2x to the 7th power divided by 7. There's x to the 7th power divided by 7 plus c. You can't forget that. All right, if you get a scenario with two different terms, 10 minus 10t, then we're going to integrate both individually. This 10t has a t to the 0 on it. So when we integrate 10, that n value is 0. We're going to add 1 and divide by 1. So this becomes 10 t to the 1st power divided by 1 is the same as 10t. We got a negative 10t over here we need to integrate also. So that negative 10 times the integral of t would be t squared over 2 divided by 2. And that becomes negative 5t squared plus c. All right, what about half? What if we have this raised to a half power? Then our n is going to be 1/2, and n plus 1 will be 3/2. So I started with a negative 3/2 out here. All right, so that's the coefficient, so negative 3/2. Now if we integrate that, we're going to raise this to the positive 3/2. Well, I might have made a little error here, we'll see. So this becomes a t, so the 1/2 plus 2/2 would be t to the 3/2. And we're going to divide that by 1. We're going to divide it by 3/2 here. So up top we've got negative 3/2 divided by 3/2. And if you take 1 divided by 3/2, it's the same as multiplying by 2/3. But anyway, 3/2 divided by 3/2 cancels. And I should have a negative out in the front here. I lost that negative. Okay, and of course plus c comes out in the end there. So my answer, given answer, was here wrong. It was wrong by negative. So I'd like you to try that out on your own. Remember, best practices, when you see a square root, we're going to turn that square root into 2 to the t to the 1/2. And if we're dividing by a square root, this would be the same as this little 1 plus 2. This is an inverse root, so we're going to take x to the negative 1/2. And this would be plus 3x to the negative 4. Okay, so just remember to rewrite those beforehand. Over here, when you see something like this, it's easiest right now to distribute t minus 5 times quantity t minus 5 would be, t squared minus 10t plus 25. So change that first, and now it's easier to integrate. All right, so pause this video now, try those out before moving on to the next section. And here we get on to the next section. We're talking about definite integrals. All right, so definite integrals, here, what we're seeing here is actually what the indefinite integral was pointing towards. When you define an amount, that's important. So if we define some bounds of our integral function, then what we're doing is we're multiplying the x-axis by the y-axis under the curve. And what this can give us is an area underneath an unusual shaped curve. All right, now if you've got a function, y equals 5, and we go from x equals 0 to x equals 10 or something like that, and it's easy to see that the integral is going to be the area of that square. Okay, so finding integrals, sometimes all you have to do, if it's easy enough, you can just use some geometry to figure out the area in that shape. Or what if it were a function like y equals negative x plus 5? Negative x would be a negative slope. So in that case, that would be the function. And if we find the area from 0 to 10, then we'd be finding the area of this triangle. Okay, so that would be half base times height. So that's kind of easy. But what do you do with a function like this? You need to use some calculus. You need to integrate. So if there is a function, x to the 5th power, and we're trying to take that from x equals 1 to 2, then you integrate x to the 5th power equals x to the 5 plus 1 divided by 5 plus 1. And then your result is, 1 over 6 x to the 6th power. And the symbol we write is this little thing, a little line saying we need to evaluate this between x equals 1 and x equals 2 and find the difference. So that becomes, we're going to plug in 1 over 6 and plug in 2 there, 2 to the 6th power, and subtract 1 over 6 times 1 to the 6th power. So that's a little messy there. That's what this is illustrating in the example. You plug in your bounds, find the difference, and that difference is the exact area under that segment of the curve. So that's what your job is down here. Now keep in mind, these answers, because it includes things like A, your answers will include A as well. Treat that like a constant. It will be in your answer, in your response. So when you solve this out, you might get something like, I don't know, 2/3. I'm sorry, this would be like a squared x squared plus 3/4 x to the 4th power, and you'll plug in a 2 for each of the x's, but leave the a alone. So your answer over here for number 9 should have an a within it. Well, I hope this gets you started. Please use other students in your class who have taken calculus if you haven't done this yet, and just use them as a resource. Please invite them to come in and help. And of course, always check with your teacher if you need help. I hope this has been helpful.